CPU Part 2. In this nugget, we continue our discussion of the CPU, or Central Processing Unit. This is Part 2. We start off talking here about CPU technologies, and we will discuss with this a number of different things such as overclocking, hyperthreading, whether or not you're going to use certain technologies such as dual core, tri-core, quad core, what throttling is, a lot of those different things such as microcode as well. We also discuss here cooling the CPU and overclocking. These are kind of related items because if you overclock, the CPU is going to get even hotter, so you need to be very careful that you protect it with a proper cooling solution. And then we also talk here about various types of sockets. Although there's too many to really memorize, there's some key ones that I think will be important for you to understand. These are just the sockets that actually receive the processors in the installation. And then there's CPU upgrades. There's some things to keep in mind, such as the version of the CPU that you're using or the stepping of it, whether or not the motherboard actually supports a CPU upgrade that you want to do, and so forth. But one of the key things you'll need to understand here, though, first of all, is some of the key CPU technologies that are important in performing an installation. So let's also review some of the other things we talked about here in CPU technologies. One of those was hyperthreading. Remember, that's where I might have a single processor, and it's actually a single core, not a quad or a dual core or something like that. But because of the two ALUs that are inside of that, it can be interpreted by Task Manager and the operating system as having two separate processors. So it kind of thinks that it's a dual core when it's really not. It just kind of tricks it into thinking so, and then threads can be attached to each one of those ALUs, for example. And then there's also literal dual core, tri-core, or quad core. And this is where, again, we can have a single processor, and you can have four independent and yet fully capable processors in that same physical form factor that we used to have only a single processor in. And then there's another one here, also known as throttling. Now this actually has a couple of different implementations. Or advantages, actually, and that would be that if I am usually on a laptop, and that's normally where you're going to take advantage of throttling. Let's say that I'm barely doing anything. Sounds about like an average day for me. Anyway, so I'm barely doing anything on this laptop. Maybe I'm just checking a little bit of email, and maybe it only needs to use 3 or 4% CPU utilization. And if I want to get an eyeball view of that, I can go back again here to Task Manager and go to the Performance tab. And I can see, right now, just recording. I got a couple other applications going on. I got Photoshop. I got a virtual machine running. And, I'm only using 20%, something like that here, and it's really not that bad. So what could happen with throttling, especially if it's lower than that, usually like under 5%, is that it'll notice that, hey, this guy's hardly doing anything. He's not very productive, is he? So what we'll do is we will give less energy to the processor, and we will throttle it down. The advantage for that, especially with something like a laptop, is that since it's using less energy now, it's also going to make the battery life last longer, and it's also going to run a little bit cooler because the more energy you apply, more electricity you apply to that processor, the hotter it's going to get. There's also microcode, which we don't need to get into, too elaborate, but just in summary here for the beginning of that. With MMX, this was multimedia extensions that Intel came out with, and AMD had some equivalents of this as well. And this would take functions that would normally have taken place. Let me go back to this picture here. Multimedia functions and interpretations that would normally have to be processed through the ALU. Well, it offloaded that, and it puts that instead onto kind of an accompanying chip. Could be on the same form factor as the actual main CPU, but it's separate circuitry here, and that might be an MMX chip or chipset, or it could be an SSE set as well. And SSE stands for, it's kind of a weird acronym, but it stands for Streaming SIMD Extensions. But the main idea here is not what the acronyms mean. The main idea is that these two technologies will, and your processor is going to have one or the other. It doesn't use both of them. This is a little bit older. But the processor is going to use something like SSE to handle a lot of those multimedia instruction sets, so it offloads the burden from the main CPU and puts it onto its own chipset down here. And that's an advantage in that it's going to give the main processor a little bit more performance than it would otherwise have had. And there's also, again, overclocking. We've talked about that before. Things to remember with overclocking, and the key things there are going to be performance is going to increase. Okay. But you're also going to get more heat, so you need better cooling solutions. Okay. Other thing with the overclocking is stability. If you get a little carried away you can overclock your system stability. You can overclock your processor to the point where every time you turn on the computer, it's just going to blue screen you. Or it could potentially get so hot that it will just suddenly and unexpectedly shut down. And I don't mean a graceful shutdown like, you click on start and shut down and it tells you it's shutting down. I mean power goes off like immediately, which can be very destructive to any open files that you had and to the operating system files themselves, so it can corrupt your operating system. Overclockers, what they'll typically do is they will overclock to the point where it reaches instability, and then when it starts to crash unexpectedly, they'll go back into the BIOS, and of course, hopefully they've made backups just in case something gets corrupted. Then they'll go into the BIOS and they will change the overclocking setting to what it was just before it started to become unstable. And again, motherboard manufacturers like Asus, which is what I use, they have UIs that you can use from within Windows to kind of customize that yourself as well. I'm kind of lazy, so I don't really go through all of those steps. I just have, the Asus overclocking utilities actually run kind of self-tests on the machine, and it can reboot multiple times to check for stability and things, but I like to use that. It really works pretty well. But anyway, the overclocking again also is a multiple of the front side bus. Remember where I was telling you if my front side bus is 800 megahertz, then if it's a factor of 4, then it's going to be able to take advantage and use the 3.2 gigahertz capability of that processor. But if I increase it to 5, if I increase it to 6, then I'm going to get potentially 4 gigahertz or 4.8 gigahertz out of that processor. Other CPU technologies that you have is what we talked about before. Your cache, like level 1, level 2, level 3, advanced transfer cache. Those sorts of things. Right now, like I said before, I've got an 8 megabyte cache, which is relatively large. And then we also have voltage regulator modules. I didn't actually discuss that before. Let me go back to my earlier photograph because I forgot to mention that. Oh, let me actually bring up a couple of photographs here that I'll show you. And one of those is going to be this one right here, where it shows you the heat sink that's on top of that processor. I took the cooling shroud off, and look at how large that thing is. That's got to be 6 or 8 inches large. It's got all these cooling fins, like I said, kind of like on a lawnmower that you'll see sometimes. And then if I go back over to my other item that we looked at a little bit earlier here as well, then if we take a look at the spot for the 2 processors, we'll also notice that there's an additional item there. It's a little bit hard to see, and it's almost goes without noticing it at all, but it's this slot right here. What in the world is that? Well, we don't really use those very much, again, in consumer level PCs, but if I put 2 physical processors into this motherboard, then they kind of have to play nicely with sharing power back and forth between the 2 of them, and I mean electricity. So the voltage regulator module is designed to help them negotiate that power back and forth. And then we also talked about the speed as well. And again, this is somewhat a summary of things I've talked about before. I just want to make sure I write it down here for you. But the speed, for example, of 3.2 gigahertz is some kind of a factor of, or a multiple of, the front side bus speed. Okay, and then we also have things like the 32-bit or 64-bit processors. Again, almost anything new that you buy now is going to be 64-bit processors. And if you can, you should try to use a 64-bit operating system as well. I mentioned this a little bit earlier about the fact that some of the applications will be able to take advantage of multiple processors as well. However, many applications are still not able to take advantage of 64-bit processing. For example, Microsoft Office, Microsoft's own products are still running at 32-bit. Now you can get certain things that run at 64-bit. For example, let me go back to Internet Explorer, for example. If you install a 64-bit operating system like Windows Vista, then it'll show you Internet Explorer in both the normal version and a 64-bit version. But other than that, there's not very many applications out there. Photoshop that we're working with right now that I'm showing these whiteboards on, I've got that in 64-bit edition. Lightroom is also available in 64-bit edition, but these are very CPU-intensive applications. Most other apps do not take advantage of all 64 bits. Now let's also take a look at how we're going to cool that CPU, especially if you're doing something like that overclocking we talked about earlier. Okay, so to keep it all cool, you can use passive methods or active methods. Almost always nowadays, passive methods are not really used anymore. On some of the older processors, you might see a heat sink on top of the processor that didn't have any fans on it, didn't use liquid cooling of any kind, it just sat there. And just by the fact that it was made of some kind of an aluminum material and with fins on it, it would just dissipate the heat. But processors really run too hot even without overclocking right now to use passive cooling, so we don't really see that much anymore. You're more likely to see active cooling in just about every respect, except for, let me go back to passive cooling. The only time you might not see passive cooling is on some motherboards where over the I/O controller hub or the North Bridge, where there's a lot of traffic that goes through it. That's actually a set of chips on the motherboard that actually do also get pretty hot. Many of them will still use passive cooling. Again, it just has a heat sink on top of it that just might have, if this is the side view of it, it might have, fins on it that stick out that cool off and everything like that. But the active cooling here is more likely on the CPU, and that's where you're going to use something like fans. So if I take a look at a CPU heat sink right here, let me zoom in a little bit on this. We can see that we still have a heat sink, and the heat sink is just kind of a block-shaped device that you put over the top of your actual processor, and it blows and it dissipates heat away from the processor by using these cooling fins, like you can see right here. And in this case, and most of the boards are like this now. Most processing solutions are like this now. It'll also have a fan on top of it that'll blow cold air down on top of these cooling fins to make it even cooler. Oh, here's a good example of what I was talking about earlier. The North Bridge, or the I/O controller hub, this has its own cooling system on top of it as well in this particular motherboard because it gets extremely hot. But both of these would be classified as active cooling solutions mainly because of the fans. And then there's also the liquid kind of cooling that you might see. That's what I'm actually using on top of the processor that I showed you earlier that I'm actually using to record this video. With this one, we have a liquid-cooled heatsink. Let me zoom out a little bit so you can see it. This particular one's made by Corsair. This is actually a fan, like a radiator, that I put over one of the case locations where it can draw cool air in. There's a little screen on the front of the case, that's a metal mesh cage, and it pulls in cool air through this radiator, which has liquid circulating through it. The liquid circulates through the tubes here, goes into this device, which is attached directly on top of the CPU. Okay, there's actually some thermal grease, which we also can call thermal compound or thermal paste. They're all the same thing, but it's on the bottom of this. It's kind of a gray putty-like substance, and it presses down on top of the processor. Well, the cool liquid that flows through this helps to cool off that processor, especially if you're overclocking, which is what I'm doing here. And then all the rest of this that you see there, these brackets here and everything, these are just a couple of different varieties. Let me zoom in again. A couple of different varieties of attachment devices you can use depending on the manufacturer of your CPU and stuff. It's made for multiple different kinds of CPUs that go into multiple different kinds of sockets and so forth. And then some screws to hold it all together. So this would be an active cooling solution as well, but it would be a liquid-cooled solution. A lot of the overclockers that are really crazy about this kind of stuff, for their liquid cooling, they'll actually sometimes use transparent tubes. It'll have kind of a fluorescent-looking liquid that flows through it, and they have black lights inside the case, and all the cool kids are tuning up their cars, and putting lights underneath their cars so people can see them driving down the street at night and stuff. Us overclockers are putting in liquid-cooled systems with fluorescent black lights so that we can see them and nobody else. Maybe Grandma, if we've got our computers in Grandma's basement. But other than that, not much. And then here we just have a photograph of the BIOS setup routine that I used a while back on an older motherboard to do some mother clocking. Did I just say mother clocking? Gosh, I don't know what I was trying to say there. I'm a mother clocker. Anyway, I was doing some overclocking with this, and I went up to 5.5 actually, and it started to blue screen me every time, so I backed it down to 5. And you can get an idea here. This is just for your example here to see some of the different kinds of things you can work with there and one of the rudimentary ways of overclocking. A lot of these are right now are a lot more elaborate than we have with this. Also, when you do overclocking, you may also have to synchronize and work with the memory modules as well, because they have to be able to keep up. That's why on the overclocking item we see here, there's also something in the background here. Let me move my pen over. DDR voltage. So you may have to crank up the voltage for the memory as well. Now, when you actually install a processor into the motherboard, it needs to go into a socket. Now, in the old days, there were also slots, and I don't think there's gonna be on the A+ exam, but just in case you see a customer come in with an older one, I'll briefly address this. You might have a slot in the motherboard. Notice that there's no rectangular location here where you would normally put a processor in current motherboards. In this particular case, it actually went right here. That's where the processor went. You would think that it would be an expansion card or something, the way that's shaped. But when you take a look at the processor itself that would go into that, now it starts to make a little bit of sense. These are single-edge connector cards, and they would have a notch here so that you could not put them in backwards and all. And this used to be a design that was implemented by AMD, and Intel also had some of these as well, but not too many. These kind of had a short life. They didn't last too terribly long in favor of other socket designs, which I'll talk to you about next. Then another kind of design you might see would be a pin grid array, and this corresponds, of course, with what's on the processor. So if I take a look at a processor like this older Pentium 4, if we push in a little bit, you can see here, kind of losing resolution a little, but you can kind of see here that this is a bunch of rows of pins. Notice that they were also lined up straight across from one another. Okay, they're not staggered in any, except my line is kind of staggered, but they're otherwise not staggered at all. They're in perfectly lined up shapes. And the reason why that's important is because that will contrast later on with something called a staggered pin grid array. But another thing to notice about this one as well is it uses a flip chip design, which is where these chips are actually visible. AMD used a similar thing as well, where you can see here that a lot of the chips on the processor are actually visible and actually somewhat vulnerable. Notice that this also has some rubber bumpers on it, and these were designed to help protect the chips from the heatsink, because with the Intel processor I just showed you, and this one as well, a lot of the heat sinks that you push down on, you really have to apply a lot of force. And it sometimes would cause the heatsink to come into contact with these chips and to cause problems or to damage them or to crack something. And by the way, the goo that you see on there, that's just some thermal paste that was put on this particular processor to prepare it for its heatsink. So anyway, this is one kind of design that we don't really see much of anymore. The flip chip pin grid array, where the chips are flipped out here, was just kind of retired because of the dangers of damaging that chip. But that was the pin grid array, and you can see again that it just had a bunch of pins on the bottom of it. And there was also the staggered pin grid array. And if we take a look at the bottom of the AMD, we can see that it did use that. Notice that these don't go straight across like I showed you on the Intel one. Okay, notice that these are, it's kind of like, they don't go straight across at all. And the reason why they did that is because that way, when they stagger these, they're able to cram more pins in to the same space here. And so that was just another design that was used for a while. Now let me return to this and catch up on a couple of other things here before I go on. And I would be aware of these things that I'm about to tell you, because you will possibly see customers with these, among other reasons. For AMD, I think some common things that you're going to see there. Number one is a socket A. Socket A. And inside of a socket A, the processor that goes in there would be an Athlon, anything in the Athlon family. Oops, too many A's. Athlon or Athlon XP would be another one of the chips there. And the way I remember that is Athlon start with A, and they go into the socket A. Okay, so the A corresponds, makes it a little bit easy to remember there. Now, this was 32-bit processors, but if you wanted to go to 64-bit AMDs, then you might have very commonly for an Athlon 64 in this case, Athlon 64, you'd very often have the 754 socket. I would remember that as well. 754, maybe this will help. 754, 64. Make that correlation. Do be aware of that one as well. For the Intel processors, let me make some more space here. For Intel, there's a number of different ones there as well. In fact, there's so many different sockets that you're not really expected to memorize them. But these are some key ones that I would keep in mind. For Intel, you would very often have a LAN grid array, or an LGA 775. That's a current kind of a socket that I'm using, in fact, to record this video with my processor. So new systems are likely to have this or some form of that. And then there's another one that's a little bit older, but it still works, and that would be a zero insertion 4 force or ZIF socket. And one of the common designations for that one would be the 478 type of a socket. Okay, so just be aware of all these things that I've written here on blue, especially when you try to know what you need to know for being an A+ technician. And then if you actually look at the sockets for these, let me try to find an example here. If I look at the actual, that's the wrong one. Let me go to this one here. There we go. This is a socket here that uses the kind of processors for a staggered pin grid array. And you can see here that they're not lined up perfectly straight across. Okay, notice that these are indeed staggered as they go across. And you would drop the processor in here. Now, notice that there's also a keying on this. Notice in this corner, there's a pin all the way to the corner. In this corner, there's a pin all the way to the corner. This one, there's not. Okay, so it's kind of it goes straight across here, across these last 3 pins. This one the same. There's not a pin in the corner. It goes straight across right there. Okay, so the reason why that's that way is so that you don't accidentally put the processor in, sideways or backwards somehow or something like that. In fact, a lot of times for electronic stores that sell motherboards and processors, they'll know that the consumer has put the processor in the wrong direction if they see one of the pins has made a little dimple right here, because they've tried to force the processor in here, and then it's not supposed to go in the orientation that they've put it in there. And so then they'll see a dimple there, and they'll likely refuse to take this motherboard back or the processor back if the consumer's trying to return those products. Don't ask me how I know about that, by the way. Anyway, this is how it would look when you don't have a processor in it. Of course, you have a lever here that you would flip up, and then with a 0 insertion force socket type, you would drop the processor in here, provided you've oriented it properly, and it doesn't require any force. It's just gravity alone will cause it to plop into place. Once that's taken place, then what you'll do is you'll see the processor, in this example, is laying down flat on this. Then what you'll do is you'll take this little lever and you'll just lock it down here, and then you'll see that it's then locked into place and applies pressure. It actually has a kind of a grid where those pins go, and it shifts it into place where this lever will move that whole platform into place and put tension on those pins when this processor is installed properly. And then finally, and again, this is more common here, you would have a land grid array, and this is the type that this Intel LGA 775 is right here. That's what I'm using on this motherboard for this type of a processor. Now, this is the top of the processor. On the bottom of the processor, it looks like this. And there's really no dimension to this. Even if I zoom in, you really don't see much dimension. And why? Because this is really mostly flat. These are ball grid, land grid arrays. These are actually little balls that have very little dimension to them at all, but they go into this kind of a socket, and we don't use pins anymore. You see, those pins a lot of times are very fragile, easily bent back, and so forth. Well, these are just lands, L-A-N-D-S, where the bottom of that processor just rests on top of these, and it makes it much easier to install. It's still keyed. If you look at the corners, you can see some differences in all the keys there. Okay, so you don't install it sideways or something like that. Likewise, again, in this case, we'll also take this cover here. There's a rectangular metallic cover that you can see here that you'll then drop over the top of this. That helps to protect it also against the heat sink. And then you'll have this lever here which also comes down and locks into place in somewhat similar fashion to what I showed you a moment ago with the other type of a socket. And then finally, let's talk about CPU upgrades. Now, this is upgrades, but it can also be like a clean install, like you have built a computer from scratch. Okay, so it's kind of the same in both instances. But let's say that you want to, upgrade your processor, where you already have an existing computer to begin with. Well, you could decide to go multi-processors if you have room for multiple processors on the motherboard, or more likely these days, you might have multiple cores, and that might be certainly an option for you as well. You do have to check with the motherboard specifications. Look at the manual that came with the motherboard, see what kinds of processors it supports. I would also definitely go to the web, because very often the web will have updated specifications for that same motherboard. And one thing that's very important with this is that, especially if you check the web and it has something different than what the motherboard specs in the printed manual have, then very likely you're also going to need a BIOS update. This is very often the case if the web says it'll support the newer version of a processor that you want to install, and yet, even though you have put it in properly and everything, when you start up the computer, nothing happens. It just refuses to boot entirely. It may be a black screen entirely. It may not even power on. If that's the case, or if it powers on, but you get a lot of beep codes generated from the BIOS, just a lot of beeping going on for error codes, then chances are you need to update this BIOS. Okay, I would be very aware of what I just told you there, because very good chance that you will see that on the technicians table. Okay. Also, we check the stepping of the processor as well. And this, again, is also probably more of a server issue. You'll see it on the Server Plus exam, I'm sure. But you'll see some designations that are very specific to this processor, like this. This is the stepping of this processor. There may also be utilities from a manufacturer that will identify uniqueness about this processor as well. But you see, even though this is an i5, let's take a look at it. It's an i5 750. I might go to the computer store and buy another i5 750. But the stepping might be slightly different. There could be incremental or slipstream changes or upgrades or modifications to this processor that were not present in a previous version. So if that's the case, I need to make sure that the stepping that's printed on there, or that I can identify, is going to be exactly the same on the upgrade, or if it's going to be a multi-processing solution, that both processors that I've installed are the exact same stepping. And also, and again, this is possibly more of a server issue, but also check for voltage regulator modules. You probably will have to buy one of those from the manufacturer of the motherboard in order to get that. Now, some things I want to talk to you about as well here when you do your upgrades, and we talked about this a little bit previously here, but especially if you're going to do something like overclocking, you're going to need to make sure that it's cooled properly. Now, when you do use a good cooling solution, that will increase the performance of your system because it allows you to overclock, and it will also increase the chip life of the processor. But when you put the processor in the socket, let's say it's in the socket right here, then what you'll want to do also is to install or to spread onto this that thermal compound or paste. It's kind of like a really tiny tube of toothpaste, and you get that from your electronics store. And I usually, you kind of eyeball this, and experience will tell you eventually how much to put on there. But I usually just put on, like that much, maybe the size of a pea. What you want to do is you want to put enough on there so that when you press the heat sink down on it, it will spread out, all the way across and cover that processor. You might get a little bit oozing out of the sides, just not too much. A little bit you can clean up, okay, with a Q-tip or something like that, or probably something lint-free would be preferable actually. But clean that up, and then you'll be fine. One thing you want to make sure of is that you don't, when you put it on there, that you don't do something like that would potentially, oops, I went too many, undos there. That you don't do something where it would create an air gap anywhere. Because if you put it down incorrectly, let's say I put it in a circle instead, like a donut shape, maybe I just round it like this. That leaves an air pocket here in the middle. Air is a great insulator, which could actually build up heat. So you don't want to leave any air pockets in that. That's why I put it down in just like a straight blob here and allow it to spread out to the edges. And then we'll go on top of this is your heat sink. Now, some heat sinks have this thermal paste already on it. It's kind of pre-packaged and pre-manufactured at the company. That's the case with my liquid cooled solution that I showed you earlier. It had some thermal grease on the bottom of it already, so I didn't have to be careful about how much of this to gauge. But if you do eyeball it, then you just have to be careful with it. And then other things that will help this as well is, once this is inserted into the case, then, if this is my tower case right here, and here's my, my motherboard and my processors right there, you'll also have cooling fans on the front of this that suck air in and that blow air inwards. And that's another important thing to keep the system cool. And I would be aware of this as well, that case fans in front of the case will force cool air across the motherboard, across the heat sink, across your memory, and across the rest of it. In this nugget, we continued our discussion of CPUs. This was part 2, where we talked about CPU technologies. Remember, we talked about hyper-threading. We talked about multi-core technologies, all these types of things. We also talked about cooling the CPU. Remember, if you want to overclock, that CPU is going to get hot, so to protect it and to allow yourself to go a little faster with overclocking, you need to adequately cool it. It's also going to extend the life of the chips on that CPU. We also took a look at the various types of sockets, and all the older processors, some of them used slots. Almost everything is a socket nowadays. There's only a few that you need to really be aware of because they're more current right now. And then also we took a look at CPU upgrades, what you do if you're installing or building a computer from scratch, or if you're replacing or adding an additional CPU. It's really fairly simple, but you do have to make sure that you properly apply that thermal paste, or thermal compound as it's also called. Well, I hope this has been informative for you, and I'd like to thank you for viewing.